In this video, I'm going to demonstrate the use of an AC induction motor as a generator. Now you can do this with any AC induction motor very simply by connecting that motor to a power grid, allowing it to spin as a motor, and then taking some mechanical prime mover like an engine and forcing that motor to spin faster than its synchronous speed. So for example, for a typical 1725 RPM motor, its synchronous speed is 1800 RPM. If I then force it to spin faster than 1800 RPM while connected to a power grid, it will function as a generator and pump energy into that power grid. The trick, though, is how to make this happen when I'm not connected to a power grid. This is called self-excitation. And the way this is done with a three-phase AC induction motor is to connect a capacitor bank to that motor. In this case, I have three capacitors, 20 microfarads each, non-polarized Mylar capacitors with a high voltage rating. They're connected directly to the three-phase lines of this motor. As I spin this motor, there's going to be some residual magnetism in its rotor, and that residual magnetism will make a small amount of voltage in the stator windings. Now normally this small amount of voltage is not enough to do anything useful with, but connected to the capacitor bank, what will happen is that capacitor bank will in essence act as a kind of a standalone power grid, a place for that energy to go into and be reflected back and allow the voltage in here to build up almost in the same way as if it were connected to a real live power grid. I say almost because, well, as we're about to see, the voltage regulation in this case is going to be very poor and has some interesting characteristics. So I just want to demonstrate how this works. Now to spin this up to speed, I don't have an engine, but I do have another electric motor, an identical motor, connected to a VFD, connected to a wall socket. So I'm using this as my mechanical prime mover to move this motor to demonstrate its use as a generator. So here we go. What I'm going to do is turn the VFD on and increase speed. And you'll see here a very small amount of voltage being generated. 0.2, 0.3, 0.4 volts AC. It's 1 volt, 1.5, 2 volts, 3 volts, 4 volts, 10, 12, about 12.6, 12.7 volts here. I'm spinning it at just over half speed. This is showing me the hertz output of the VFD. Normally 60 hertz is full speed. In this case, it's 32.6 hertz, so I'm a little over half speed, somewhere in the neighborhood of 900 RPM. I'm generating about 13 volts. Not very impressive. But watch what happens as I speed it up just a little bit more. Suddenly the voltage shoots up and easily exceeds 120 volts. Now this is very poor voltage regulation. As I turn the speed up and down, even slight increases and decreases have large impacts on the amount of voltage. And if I connect a load to this, the voltage sags very dramatically. In fact, I can connect such a heavy load that the excitation stops and the generator's output basically goes down to zero. But I think this is impressive nonetheless. The ability to have a AC three-phase squirrel cage induction motor act as its own generator with no connection to an outside grid. This is truly self-excited.